Hi, everyone. In this video, we will conclude our discussion of derivatives of scalar fields by finally looking at a classification of stationary points of scalar fields. Before we begin, I want to revisit some definitions that are definitions we saw in 5610, and you could probably figure out how to extrapolate them to the case of scalar fields, but let's take the time to step through this. So I want to define a local maximum and a local minimum of a scalar field. So if F is a scalar field defined on some open set S in Rn, then we say that F has a local maximum at A if there exists, so we have there exists some r greater than 0 such that f of x is less than or equal to f of a for all x in the ball of radius r around A. So said another way, f of a is the largest value that the function f takes on this neighborhood of A. So if there is some neighborhood of A such that f of a is the largest value f takes on that neighborhood, then we're at a local maximum. And similarly, for local minimum, we define it in a similar way. We simply reverse the inequality here and say that f has a local minimum at a if there exists an r greater than 0 such that f of x is greater than or equal to f of a for all x in the ball of radius r around A. So again, these are nearly identical to the definitions we saw in Math 5610 for defining a maximum or a minimum value. Notice, again, these both have equalities, right? So if you're at a you say you have a constant function, so f of x, y is equal to 3, then every point is both a local maximum and a local minimum. That's okay. We want to allow that to happen, but we define these in exactly the same way. The only things we have to change are, again, really here, what we're changing is what our open sets are, right? What our open neighborhoods look like in Rn. And so this just replaces an interval around A, right? We now have a ball of radius R. Now, collectively, right, we refer to the local maxima and the local minima of a function as the local extrema of the function. So if we say something is a local extrema, we simply mean that it's either a local maximum or a local minimum, or possibly both. So again, we could probably have just started saying the words local maximum and local minimum, but just to formally define those things before we move on, we'll just see that they're defined in exactly the same way. All right. Now, if I think back to like Math 5610 or just Calc 1 even, right? When I want to define local maximum and local minimums of a function, what did I do? Well, first I would find the critical points, then I would test critical points to determine whether they were local maxima, local minima, or neither. Okay. Now, we want to do a similar thing here. Okay, so we want to be able to find critical points and then classify them as either local maxima, local minima, or neither. Okay. So in this point, we need to define what a critical point is. Now, again, it's going to be nearly identical to critical point from, say, Calc 1. But let f be a function which is differentiable on some open set S. A point A is called a stationary point or a critical point, so those mean the same thing. The apostle text tends to use stationary point more often. I will probably use both. But a point A is called a stationary point or a critical point if the gradient of f at that point is equal to 0. Okay. So let's first, what does it mean for the gradient of f to be equal to 0? Now remember this gradient, right? That's a vector quantity, and that is simply partial derivative of f with respect to the first variable at A. Partial derivative with respect to the second variable of f at A, all the way up to the partial derivative with respect to the nth variable at A. And we're saying that this is equal to the 0 vector. Okay? So really, here, the first thing we notice is that we're really saying that all of the partial derivatives are equal to 0. But you'll notice also here that we only define a stationary point or critical point at a point A where our function f is differentiable. Okay, so since f is differentiable at A, this also implies that all directional derivatives are zero. So all the directional derivatives, say f prime of A with respect to y, these are equal to zero for every y, right? So when we're at a stationary point, really the best way to think about it is that it's if we're thinking of a function from R2 to R, right? At a stationary point, the tangent plane is is parallel to the xy plane, right? So we have a perfectly horizontal tangent plane at that point. Now, this is maybe a little different. Different calculus books handle critical points slightly differently. So, whether critical points are required to be in the domain, whether critical points include places where your function is not differentiable, right? Those all can vary slightly book by book. So I just want to emphasize here that we're only defining a critical point to be a place where the gradient vector is zero, okay? And where not only is the gradient vector zero, your function is differentiable at that point, right? Because remember, all of the partial derivatives existing does not necessarily even imply that your function is differentiable. So we're saying not only that your partial derivatives are all zero, we're also saying your function is differentiable, therefore every directional derivative is zero. All right. So in some ways it's the same, but a little more nuance here in the case of a generic scalar field. Now, one thing you can sort of already see, and in fact, one of the homework problems deals with this. If I have a local extrema at some point A, and my function is differentiable at that point A, then A has to be a stationary point or a critical point. So if I know already that I'm at a local maximum or a local minimum, then my gradient must be zero at that point, assuming that my function is differentiable there. Okay, so one of the homework problems asks you to show this for either a maximum or a minimum, right? But this is sort of a necessary condition. If I'm going to be at a local extreme value, then this gradient has to be zero. The harder question is, if I'm at a stationary or critical point, how do I know what kind of local extreme value how do I know whether I'm even at a local extreme value? And if I am at a local extreme value, is it local maximum, local minimum? How might I classify it? All right, so we will not prove this theorem in part because one case of this is a homework problem and the other case is nearly identical. So we won't prove this, but I just wanted to remind you of that fact here. Now, when we start thinking about the things that can happen, even if I just think about functions from R2 into R, you can probably start to visualize some examples of local maximum and local minimum values. So you can imagine this sort of paraboloid here, which has, at some point, so imagine I'm in R3 here. Okay, so at this point A, right, I have a local minimum value, right? And again, just to emphasize visually some points of that definition, right? This is a local minimum. This is actually a global minimum, but it's a local minimum because I can find some little neighborhood around A such that if I look at all of the function values, so that whenever I map these x values up, all of these function values are greater than or equal to the value of the function at A. Okay. Similarly, I can. So now I'm going to draw a slightly more complex figure. So let's say I have a surface that looks like this. Okay. So you can sort of imagine this is, sort of looks like a saddle. Here, whatever this point is, right, A, in my domain. I have a local maximum here. Again, here this is also a global maximum. If I look here at this point, at this A value, I have a local maximum, right? So I can find some neighborhood of this point so that all of my function values here are less than or equal to f of a. But if I try to make this circle too big, right, I'll start capturing points where my function actually takes on larger values. Okay. But here, even in this case, we can see this other example. So we also can have saddle points. So if you imagine looking at this point right here, okay, now this cannot be a local maximum, okay, because if I take any neighborhood of this point, right, and I map it up here onto my surface, let me actually use it. So if I take any neighborhood of this point, I map it up here onto the surface. The best way I can describe, right, this, if I think about this piece of the surface it maps up to, it looks like a Pringle, if you've ever seen the chips, the Pringle, right? So it's sort of arching here up, and on the sides it's arching down. So no matter the size of this neighborhood, this can't be a local maximum because there are going to be some points over here, right, which are above my point, and it can't be a local minimum because there'll be some points over here that are smaller. Okay. So this is neither a local maximum or a local minimum, but my gradient is 0 here. If I think about the tangent plane here, right, it needs to be a horizontal plane, right? It needs to be parallel to the xy plane here. Okay. So if we have a stationary point of f, and that stationary point is such that every neighborhood of that point contains points that are larger than f of a and smaller than f of a, then we call that a saddle point. So again, a saddle point, a stationary point is called a saddle point if every neighborhood of the stationary point contains a point x where f of x is greater than f of a and a point y where f of y is less than f of a. Okay. It says points, in many cases, there'll be more than one, but you really just need to show that for every neighborhood, there's at least one point x such that f of x is greater than f of a, and one point y such that f of y is less than f of a. Now, you could argue that we either do or don't have these if we just think about functions from R to R. I think it's sort of fair to say that we do have these, they're just slightly different. If you think about, so you probably would have called these inflection points in a calculus course. So at this point, right, you had a derivative that was equal to 0, right? But if you take any little neighborhood of that point, okay, so if we take any neighborhood of this point, some of our function values are going to be just above f of a, which is 0 in this case, and some of our function values are going to be just below that. Okay, so in some ways, a saddle point is somewhat analogous to an inflection point from Calc 1 or from Math 5610. All right. So again, now we have another thing, another sort of classification of what can happen near or at a stationary point. And so again, the question is, if I have a stationary point, now I know, okay, it could be a local maximum. It could be a local minimum. It could be one of these things, these saddle points, which are not a local maximum or a local minimum. Or it could be sort of something else entirely, right? Or at least, right, I might not be able to tell from my particular test. If you think back to a lot of these tests from calculus, like my test may not reveal to me what it is, right? So what we want to see is if we can develop some sort of test that will tell us, in these cases, I get a local maximum. In these cases, I get a local minimum. In this case, I get a saddle point. And I may have to deal with a case where the test is inconclusive. I may still have one of those things, but my test isn't going to reveal to me which of them I have. All right. I will say, and especially if you ever go on and teach a Calc 3 course, I've gotten a lot of mileage out of this surface. It's really nice that this surface has both local maxes and saddles. And in general, I would encourage you to try and recreate some of these functions, either whether they're functions that we draw or that we illustrate in Desmos. Some of those are difficult to draw by hand, and that's why I illustrate them in Desmos. But some of these that I draw by hand, just getting a little practice drawing some of these basic surfaces in uh, in multiple variables, especially if you're going to teach a Calculus 3 course at some point, it's very beneficial. It is a skill that requires some practice, and despite over a decade of practice, I'm still not great at it. But always a good thing to work on when you have some spare time. All right, so now let's imagine we're at a stationary point. So that means the gradient of f at a is equal to 0. Let's further imagine if we're at a stationary point, that means we're differentiable at that point. And let's go ahead and assume that we have continuous second partials in some neighborhood of the point A. Basically, we want to assume enough so that we get a second order Taylor formula, and we're at a stationary point. All right, so if we do that, we get this from the second order Taylor formula. Notice the gradient term has disappeared because the gradient is 0 there. Okay. So if I take this and let's say I subtract over f of a plus y minus f of a, then is equal to 1/2 y h of a times y transpose plus norm of y squared e of a y. Okay, and recall here that the idea is not the idea, the definition of this or the theorem tells us that this e of a y goes to 0 as y goes to 0. All right, so if I imagine what I really want to know, right, is a local maximum, a local minimum, or neither? Okay, so if I want to know, let's say I imagine I wanted to know whether just it was a local maximum or local minimum. So what is this difference telling me? It's telling me the difference between f of a and f of a plus something else. Now, if I restrict my y to be some small vector, right? And by small, I mean small norm, so close to 0, then I could look at this, and if I knew that this was, say, positive for all y, if I knew that this difference was positive for all y, then I would know that f of ay must be greater than or equal to f of a, so f of a would have to be a local minimum. So if I knew that this difference was positive for all y with small norm, then I would know that f of a is a local minimum. If I knew this difference was negative, that would mean f of a has to be larger than f of a plus y. And so then I could conclude that f of a is a local maximum. Okay? So what I really want to understand is I want to understand the sign of this difference. Well, let me do it by looking here. Now, again, remember, I'm looking near a. I'm not looking for every value of y. I'm only looking for y's with small norms. Now, with the norm of y being small, I don't really know what that implies here. But I know here, if the norm of y is small, let's say it's at least less than 1, then this quantity is going to be even smaller, right? Take a number less than 1, square it, you get an even smaller number. So this number is going to be small. And as the norm of y gets small, this quantity gets small. So it leads me to believe that I could understand this difference for small y just by understanding the sign of this term. Okay, so the idea is if we understand the sign of this term, hopefully we can make sense of the sign of this whole thing, which will then tell us something about the sign of this. Now, there's still work to be done there, but let's see if we can work with that idea. Yeah, that's sort of the train of thought we want to follow through. Now, last time, right, we defined this this y h times y of t or times y transpose as a quadratic form, right? And we looked at an important result that we're going to need to use, right, to help us make sense of that. So Again, this is just that same result from last time. So anytime I have something of the form y, a matrix A times y transpose, that's called a quadratic form. And we have this result. We didn't prove it, and we're not going to prove it. It's really a linear algebra type result. But this quadratic form will be greater than 0 for all non-zero y if and only if the eigenvalues of the matrix are all positive. And this quadratic form will be negative for all non-zero y if and only if all the eigenvalues of this matrix A are negative. Now, let me point out one other thing that we're going to want to make use of in a little bit. If this thing, because these are if and only ifs, if this changes sign, right? So if Q of y is sometimes positive and sometimes negative, then you must have not all positive eigenvalues and you must have not all negative eigenvalues. Now, there's some subtlety there. Things could be 0, but we'll see how that comes into play in a little bit. But for the most part, what we're really going to make use of is the quadratic form is positive if and only if all the eigenvalues of the matrix are positive, and the quadratic form is negative if and only if all the eigenvalues of the matrix are negative. All right, so here is the theorem we want to prove, and this is going to be sort of the main goal of the day. Okay, so let f be a scalar field. It's going to have continuous second derivatives, second partial derivatives on an open neighborhood of the point A. Okay, that basically just allows us to have the stationary, to have the second order Taylor formula, and let A be a stationary point of f. Okay, so I'm at this point, I have a Taylor formula, it's a stationary point, so the gradient is 0. Okay, and we want to prove the following three things. So we want to prove that if this Hessian matrix H of A has all positive eigenvalues, then f has a local minimum. We want to prove that if that Hessian matrix has all negative eigenvalues, then f has a local maximum at A. And if that Hessian matrix has both positive and negative eigenvalues, then A is a saddle point. Now, you might look at this and go, okay, well, great, this tells us exactly what happens. Well, not exactly, because you'll notice that this doesn't tell us anything about what happens when we have 0 eigenvalues. So if we have all 0 eigenvalues, we're not going to be in either of these cases. Now, if we have a 0 eigenvalue, it's still possible that we have both positive and negative eigenvalues, right? But for example, if I have all positive eigenvalues except for 1, and that eigenvalue is 0, this case doesn't apply, this case doesn't apply, and this case doesn't apply. So you have to do a little more sophisticated analysis in that point. So there's still inconclusive cases, even though it's sort of, if you just think in terms of positive and negative, right, it seems like we are covering a lot of them. All right, so this is the theorem we want to prove. We're going to spend a lot of time proving 1. From that, we'll basically really quickly be able to go, yeah, you do the same thing for 2, you just flip some inequalities. And then we'll briefly discuss how you would prove 3, but we might not write out every detail of that. We'll just sort of get the main idea. It is similar to 1, although slightly different. All right, so let's prove the theorem, and we're going to prove 1 first. Okay. So again, just as a quick reminder, right, 1 is all positive eigenvalues, right? So we want to look at what happens when we have all positive eigenvalues. All right, so by the Taylor formula, which again applies because of our conditions on the second derivatives of f being continuous on that open ball. So by the Taylor formula, we have that f of a plus y minus f of a is equal to y transpose, or sorry, is equal to 1/2 y h of a y transpose plus norm of y squared times e of a y, where again, this e of a y goes to 0 as y goes to 0. All right. The first thing I want to do is let me give names to the eigenvalues. So my assumption is all the eigenvalues are positive. Okay, so let 0, so all of them are positive. So I'm going to let lambda 1 be the smallest one. It's positive. And then I'll just order the rest of them. Now, there could be repeated ones. There could be all sorts of things. So I'm going to just, write less than or equal to for the rest of these. But the idea is these are in at least non-decreasing order, and they're all positive. Okay, I really just need lambda 1 to be the smallest one, but I might as well sort of order the rest of them. Okay. Now, since this is positive, since lambda 1 is strictly positive, oh, sorry, I want these to be the eigenvalues of the Hessian. Okay. Since lambda 1 is strictly positive, I can choose some u such that u is strictly between 0 and lambda 1. So what I want is I want u to be some positive number that's less than lambda 1. Okay. Now, consider the values. Now, I'm going to take each of these eigenvalues, and I'm going to subtract u. Okay. So then the n numbers, so lambda k minus u, for k going from 1 to n. So I'm just taking each of the eigenvalues, and I'm subtracting off u. Okay. These numbers are now the eigenvalues of the matrix h of a minus ui. Now, if you haven't taken a linear algebra course in a while, it might be a little tricky to see why. Essentially, you need to show that if these numbers are the eigenvalues of this, then these numbers are the eigenvalues of this. If you have taken the grad linear course already, this is something you should be able to prove. But again, if you haven't, then don't worry about this. This is just a fact that we're going to use. Okay. So in particular now, I know, and each lambda k minus u is strictly positive, right? Because I chose u so that u was smaller than lambda 1. So lambda 1 minus u must be positive, and all the other lambda values are bigger than lambda 1. So each of these things is still positive. Okay? So now h of a minus ui is a matrix with all positive eigenvalues. Okay. So since h of a minus ui has all positive eigenvalues, the quadratic form associated with that is positive. So we must have y of h of a minus ui times y transpose is greater than 0 for all non-zero y. Okay, so this is just using that theorem about the sign of quadratic forms. This is a matrix with all positive eigenvalues. Therefore, the quadratic form associated with this matrix is always positive for all non-zero y. Well, if I look at this, right, I can distribute some of this. So hence, if I just distribute the y and the y transpose, I get y h of a, y transpose minus y uh, times u I, y transpose is greater than 0, right? But if I look at this, this is y h of a, y transpose. Okay, this u is a scalar, so I can pull it out front. And then I have y times the identity matrix times y transpose. Well, the identity matrix times y transpose is just y transpose. Okay. Y times y transpose, that's just the inner product of y with itself. So this is the norm of y squared. And so what I end up with here, right, this was equal to this, was equal to this, and this is greater than 0. So I get this is greater than 0. And so that means that y h of a y transpose is strictly greater than u times the normal y squared. All right. So what is this doing? This is giving me some lower bound on this quantity. Okay. Now, if you think about it, okay, in this first case, this is a good place to pause. What am I trying to prove? All of my eigenvalues are positive. I'm trying to prove I'm at a local minimum. So if I'm at a local minimum, then I really think that this difference should be positive. Okay. So what I want to do is I want to bound this difference below by 0. So what I'm going to do is I'm going to look at this and I'm going to say, okay, well, what's the smallest this could be? It could be u times the norm of y squared. Then I ask myself, well, what's the smallest this could be? Well, that's a little trickier because this could be negative, right? I don't know anything about the sign of this. So the first thing I could imagine is, well, what if I subtract off, I change the plus to a minus, I subtract off normal y squared times whatever the absolute value of this is. Okay, but then I need to understand the absolute value of this. So that's where I can use this property that e of ay has to go to 0. Okay, so let me explain how I'm going to do that. So since e of ay goes to 0 as y goes to 0, there exists some r greater than 0 such that the absolute value of EAY, so since this is going to 0, I can make this in absolute value as small as I would like. In this case, I'm going to want to make it less than 1/2 u norm of y, or sorry, 1/2 u, just 1/2 u. So I can make this happen as long as y is close enough to 0. So that's where this r is going to come into play. I'm going to say this holds whenever the norm of y is less than r. So I can pick some r so that whenever my y is within distance r of 0, then I know that e of ay in absolute value has to be less than 1/2 times this u. Okay. So if I do all that, then when the norm of y is less than r, we have, okay, let's go back to our Taylor formula. So I've got f of a plus y minus f of a. Okay. That is by definition equal to 1/2 y h of a minus, or sorry, plus, nope, missing a term, y transpose plus norm of y squared EAY. All right. Now, again, what do I want to do? I want to show that this is a local minimum. So this thing should be positive. Okay. So let me start making this thing smaller. Okay. Well, again, one way to make this smaller is just to say, well, let me subtract off instead of adding here, since this could be negative, I'll leave the first term alone. Okay. Then I'll subtract off the norm of y squared times the absolute value of EAY. Okay. Now, this quantity here, I can bound from this inequality. Okay. So I've got a 1/2 here, but I know that the quadratic form y h of a y transpose is greater than u times the norm of y squared. So this becomes 1/2 norm, or 1/2 u norm of y squared minus, now here I've got a norm of y squared, and because my norm of y is less than r, this is less than 1/2 u. So the most I could be subtracting off is 1/2 u times the norm of y squared. And notice that that difference is precisely 0. So now by combining these two inequalities, right? So just to highlight, that's this pink is coming from here, and the blue piece is coming from here, right? I'm able to get what? I get that whenever y is small enough, close enough to 0, then f of a plus y minus f of a has to be strictly greater than 0. Okay, and so what does that tell me? That tells me that f of a must be a local minimum, right? Because for every y, right, in some neighborhood of 0, right? So if y is in some neighborhood of 0, this f of a plus y is just an arbitrary vector in the neighborhood of radius r around a. Every one of those vectors minus f of a, the difference is strictly positive. So f of x must be greater than or equal to f of a for every x in that neighborhood of a. All right, this is the proof of number 1. Now, for number 2, you repeat this. It's a nearly identical proof. So you just need to flip some inequalities. So all your eigenvalues will be negative. So you take lambda 1 to be the largest negative one, so still the one closest to 0. And you choose a u. You want it to be between lambda 1 and 0 still, but now the signs flip. And you keep going through this process. The proof will work. That's one way to do it. The way that I think is sort of the really clever way is actually to take your function f and define a new function g, which is just negative f. Okay. Well, if f is supposed to have a local maximum somewhere, right, then negative f would have a local minimum. And the Hessian of negative f is negative the Hessian of f. So you can basically just apply part 1 to the function negative f, and everything really also goes through. So there's sort of 2 ways to prove the second part. One is maybe just directly modifying the proof in fairly obvious ways. The other is a little more clever, which is just to apply the first part to negative f to get the result that you desire. Both of them will lead you in fairly short order to a proof of 2. Now, for the third part, right? And so just to remind us, the third part says if we have both positive and negative eigenvalues, then we're at a saddle point. Now, the idea here is if I have both positive and negative eigenvalues, then what I want to do is I want to pick one of the positive ones, pick one of the negative ones. Okay, and then what I'm going to do is I'm going to pick a u, sort of like I did before. But now what I want is I want to make sure. So before I had like 0 and I had lambda 1, and I picked a u somewhere in here. right? When it's negative, you have lambda 1 here, you have 0 here, and you pick u in here. Now what you want to do is you have, let's say, lambda 1 and lambda 2, and let's just say they have opposite signs. So maybe lambda 1 is a negative, lambda 2 is that, and maybe 0 is somewhere in here, right? It doesn't have to be exactly in the middle, okay? And the idea is you want to choose a u here so that u is within the smaller of these like two distances. So you measure like this distance, which is just absolute value of lambda 2. This distance is absolute value of lambda 1. And you pick a u that's smaller than both of these, so smaller than the minimum. Okay. And the reason you do that is so that lambda 1 minus u will still be negative, and lambda 2 minus u will still be positive. Okay, so you're always picking this u so that you preserve the things you want about the signs of the eigenvalues. All right. So the first thing you have to be a little more careful of is how you choose your u, but fundamentally you want to choose your u in such a way that lambda 1 minus u is negative because lambda 1 was negative, and lambda 2 minus u is positive because lambda 2 was positive. Okay. It turns out that they are still eigenvalues of h of a minus ui. Great. But then that quadratic form, so then when you go to look at the quadratic form, y h of a minus ui y transpose, when you go to look at that quadratic form in case 3, then it has to take on both positive and negative values. Why? If it didn't take on positive and negative values, either all the eigenvalues couldn't be negative or all the eigenvalues couldn't be positive. So like, if it didn't take on both, it wouldn't be possible for you to have both negative and positive eigenvalues. Again, because those statements about the sign of the quadratic form are if and only if. Okay, so if this didn't take on any negative values, okay, then there's no way any of your eigenvalues could be negative. If it didn't take on positive values, there's no way any of your eigenvalues could be positive. Okay, so that basically allows us to conclude that this must take on some positive values and some negative values. Okay. And then once you do that, you basically go through both cases of the other proof. So you say, okay, there's somewhere where this takes on a positive value. At that point, f of a plus y minus f of a will be positive, okay, which means that f of a is a local minimum. Wherever this takes on a negative value, then f of a plus y minus f of a must be negative, which means f of a is a local maximum. Okay, so the proof sort of proceeds the same, but you have to be a little careful, in sort of figuring out how you're going to pick points to show that you have some points that are giving you positive values and some points that are giving you negative values. So again, you have to be a little careful. The other case, I guess, to sort of mention here, you might wonder, like, what happens if all the eigenvalues of the Hessian are 0? This wouldn't like tell you anything at all, right? And this is sort of equivalent to when you do the second derivative test in Calc 1, you have to look at higher order terms in the Taylor series. You have to look at higher derivatives to tell you what's going on. So in the case that like all of your eigenvalues are 0, so you really can't say anything, we just have to proceed with a higher order analysis of the Taylor series or the terms in the Taylor series. All right. So if I just flip back here momentarily, this is the second derivative test for scalar fields. Okay. But if you're ever teaching Calc 3, or if you think back to your own Calc 3, your book probably didn't say anything about eigenvalues. Most Calc 3 courses don't require linear algebra as a prerequisite. And so you might wonder, well, wait, what did we do in Calc 3? So what I've done over here is I've basically given you, I've essentially pulled this out of the, if you Google OpenStax. So OpenStax is a series of open textbooks, and they have a Calc 3 book. So You can just Google OpenStax Calc 3. It's all freely available online, so you're not pirating anything. I've more or less stolen this version of the theorem from them, although it's the same version that appears in many textbooks. So they often present the second derivative test in the following way. So the first is they restrict themselves to scalar fields from R2 to R. And so they say, okay, let f of xy, because it's from R2, so just two variables, have continuous second partial derivatives. Okay, that looks right. And let AB be a stationary point. Okay, that seems right. Okay. And then they define this term D. So they say let D, which some books call the discriminant. So let it be equal to the second partial derivative of f with respect to x times the second partial derivative of f with respect to y minus the mixed partial derivative of f squared. Okay. And then they give you all these conditions. They say, well, if d is greater than 0 and the second partial derivative of f with respect to x is positive, then you're at a local minimum. If this value d is positive, but fxx is negative, then you're at a local maximum. If d is negative, you get a saddle point. What on earth does this have to do with the theorem we just proved? Okay, because on the surface, these have nothing to do with one another. Well, we might sort of get a hint by looking at this value, capital D. So let's understand why this discriminant test or determinant test works. So the word determinant test comes because if I look at that value D, so that was fxx at AB times fyy at AB minus fxy at AB squared. If I look at this, this is actually the determinant of the Hessian matrix, which for a 2 by 2, and I'm going to drop the of AB, but all of these are evaluated at AB. But again, recall, because I'm in the case with continuous second order derivatives, these are equal to each other, so I can call this f of xy also. Okay, so this is just the determinant of the Hessian. Now, what on earth would the determinant? Our theorem talked about eigenvalues. So what we need to remember are some facts from linear algebra, namely that for any matrix A, the determinant of A is equal to the product of its eigenvalues. And then there's one other piece, which is that the trace of A, so for matrix A, the trace is the sum of its diagonal entries. That's equal to the sum of its eigenvalues. Now, again, we're just in R2, so here, this is just the product of the eigenvalues, lambda 1 and lambda 2. This is just the sum of the eigenvalues, lambda 1 plus lambda 2. All right. I can also express, right, the determinant of this, right, that's just that quantity capital D. The trace here is just fxx plus fyy. All right. So if we go back to the cases of that theorem, the first case said that D was greater than 0 and that fxx was greater than 0. Okay, well, wait, what would that tell me about my eigenvalues? So if D is greater than 0 and it's the product of the eigenvalues, well, that tells me that both of my eigenvalues must be positive. Or sorry, not positive. It tells me both of my eigenvalues must have the same sign. They're either both positive or both negative. Now, this fxx, okay, if it's positive, how do I know that, like, if I knew that lambda 1 plus lambda 2 was positive, I know these have the same sign, so if I knew that this sum was positive, then I would know they both have to be positive. If I know that lambda 1 and lambda 2 have the same sign because this product is positive and this is negative, that tells me they're both negative. Okay. So what I want to note is that this determinant here, if I know it's positive, so D being greater than 0, this implies, well, I've already written D. So D being greater than 0, that implies that fxx, fyy must be greater than fxy squared. And that's something squared, so it must be greater than or equal to 0. Okay. So if I know this is positive, that tells me my eigenvalues have the same sign. Now I want to know if they're positive or negative. Well, now I know, since, again, this is positive, I know that the product of fxx and fyy must be positive. So that tells me fxx and fyy have the same sign. Okay, so if fxx I know is positive, these have to have the same sign. So fyy must also be positive. That means fxx plus fyy, which is the trace, must be positive. So now I know that the product of the eigenvalues is positive and the sum of the eigenvalues is positive. That gives me that both of my eigenvalues have to be positive. Okay. If the discriminant is, or determinant is positive and fxx is negative. Okay. Well, now all this stuff stays the same here. So fxx, fyy is still greater than fxy squared, which is greater than or equal to 0. That still tells me that fxx and fyy have the same sign, but now fxx is negative. So now fxx and fyy are both negative, so their sum is negative. So now I have two numbers that multiply together to give me something positive. That means they have the same sign, and add together to give me something negative. They must both be negative. Okay. So notice that what these cases are doing is they're breaking out and they're really giving you information about the eigenvalues. So here, since both eigenvalues are positive, this means that we're at a local minimum. Here, since both eigenvalues are negative, this means we're at a local maximum. And if you go back to that theorem, that's exactly what these said. It's just that they were hiding information here about the eigenvalues without saying the word eigenvalue. Okay. In the last case, if the determinant is negative, right? Well, that just means that these have to have different sign. And since it's not 0, one must be positive and one must be negative. That immediately tells you that one of them is positive, one of them is negative, okay, which implies I'm at a saddle point. Okay. Now, again, there's also the inconclusive case. So if you're not in any one of these cases, the only way that can happen is either this determinant is 0. That means one of your eigenvalues is 0. Okay. Or your determinant is positive, but then one of these here is 0. So if I look at that, so if this is going to be positive, but fxx were going to be equal to 0, well, then I would run into a problem, right? Because that would mean fxy is also 0. That's the only way all of this could work, okay? And then if you have that those things are both 0, so you have that the determinant is equal to 0, that means one of these is equal to 0. Let me sketch this out here. So if D is greater than 0 and fxx is equal to 0, okay, we want to think about what that would mean. So you would say, okay, the determinant is then just going to be minus fxy squared. This has to be positive though, so I have a contradiction because this is always less than or equal to 0. Okay, so in this case, really what you would end up with is that the determinant had to be 0. That's the only way that could have happened. And so we're back in that case from before. So there are still inconclusive cases. And again, but there aren't that many. And for each of those, again, you just have to do a more detailed analysis. This theorem isn't going to reveal anything for you. Okay. So this actually will conclude our discussion, at least for the time being, of sort of derivatives of different things. Now, the next thing we're going to move on to is integration. So we'll start with that in the next video. One last thing, though, to just briefly address, you may wonder, okay, we did all this stuff about, classifying stationary points of scalar fields. What about vector fields, right? Well, note that there's really no way of making good sense of what it would mean for a vector field to have a local maximum or a local minimum, because we don't have a nice ordering on Rn, right? So because the outputs of vector fields are vectors, I can't compare one to one another. I can't compare two outputs in an easy way, right? That would really allow us to think about something being a local maximum or a local minimum. Now, we will come back when we get towards the end of some of the integration stuff, we will come back and talk a little bit more about other notions of derivatives for vector fields. But we'll look at those with integration when in that context, they will make a bit more sense. So in the next video, we will begin our discussion of integration with a discussion of line integrals.